Welcome! In this session, we will explore problem number 163, titled Missing Ranges. This problem is a great exercise in understanding array traversal and working with ranges. Let's dive into the details and uncover the most efficient solutions. In this problem, we need to identify and list all the missing ranges within a given inclusive range, lower, upper. The input consists of three parts: a sorted, unique array of integers called nums, and two integers lower and upper that define the start and end of the range, respectively. A missing range is any set of consecutive numbers within, lower, upper, that are not part of nums. These missing ranges are represented in one of two formats. If the range consists of a single number, it's represented as the number itself, like 5. If the range covers multiple numbers, it's written as start-end, such as 2-4. The problem expects us to return a list of these missing ranges as strings. Let's look at an example to clarify. Imagine we're given the input nums equals 0, 1, 3, 50, 75, with lower equals 0 and upper equals 99. The inclusive range here is from 0 to 99. The numbers in nums cover 0, 1, 3, 50, 75, so we need to determine the gaps, or missing ranges, within this range. The first missing range is 2, which is the single number between 1 and 3. The next missing range is 4-49, as there are no numbers between 3 and 50. Following that, 51-74 represents the continuous missing range between 50 and 75. Finally, after 75, the range 76-99 captures the remaining gap up to the upper bound. These four ranges together, 2, 4-49, 51-74, and 76-99, make up the output. In this way, we've accounted for all numbers in the range 0, 99 that are not covered by nums. Now, consider the case where nums is an empty array. For the input nums equals, with lower equals 1 and upper equals 1, the inclusive range is 1, 1. Since nums contains no numbers, the entire range, 1, 1, is missing. In this case, the output is simply 1, because the range consists of just one number. Another example of an empty array demonstrates how the solution handles larger ranges. If nums equals, lower equals -3, and upper equals -1, the inclusive range is -3 minus 1. Again, since nums has no elements, the entire range is missing. This means the output is -3-1, as the range spans multiple numbers and is represented in the start-end format. For a more complex example, take nums equals 1, 3, 5, 10, with lower equals 0 and upper equals 12. Here, the inclusive range is 0, 12, and the numbers in nums cover 1, 3, 5, 10. The missing ranges are 0 before 1, 2 between 1 and 3, and 4 between 3 and 5. Then, the continuous range 6-9 fills the gap between 5 and 10, and finally, 11-12 captures the numbers after 10 up to 12. These missing ranges make up the output. Let's also consider some special scenarios. First, if nums exactly matches the range, lower, upper, there are no missing ranges, and the output will be an empty list. Next, we need to ensure our solution works correctly for very large values of lower and upper, especially when nums is small or empty. Finally, we must handle negative values correctly. For instance, a range like -10, -5 should be processed just as accurately as positive ranges. By addressing these edge cases, we can ensure our solution is robust and handles all possible inputs effectively. When approaching the missing ranges problem, the brute force method is the most straightforward starting point. The idea is simple: iterate through the entire range from lower to upper, checking if each number exists in the given array nums. Any number that's missing is added to the result, and consecutive missing numbers are grouped together to form ranges. While this approach is intuitive, it comes with significant drawbacks. For every number in the range, we repeatedly check for its existence in nums, which leads to inefficiency, especially for large ranges. The time complexity becomes O, upper lower, *n, where n is the size of nums, making it impractical for larger inputs. On the other hand, the optimized two-pointer approach offers a smarter solution. Instead of iterating through every number in the range, we leverage the fact that nums is sorted. By comparing each number in nums with the expected sequence starting from lower, we can directly identify gaps where numbers are missing. Missing ranges are detected only when a gap appears between consecutive numbers or at the boundaries of the range, making the process much more efficient. To implement the optimized two-pointer approach, we follow a set of clear steps. First, we initialize a variable previous to lower 1. This helps us handle the range before the first number in nums. Then, we iterate through nums, adding an additional iteration for upper plus 1 to account for any potential range beyond the last number in nums. During each step of the iteration, we compare previous plus 1 with the current number. If previous plus 1 is less than the current number, we know a range of numbers is missing. If the gap represents a single number, we record it directly, otherwise, we create a range from previous plus 1 to current 1. After processing the gap, we update previous to the current number and continue. This approach ensures we efficiently detect all missing ranges in O, n, time, where n is the size of nums, while using only constant extra space. Alternative approaches, like using a set, simplify membership checks by converting nums into a hash set, but this increases memory usage. Binary search could also be applied to locate the boundaries, but it's unnecessary given that a single linear pass is sufficient. The two-pointer approach strikes the right balance between simplicity and efficiency, making it the optimal choice for this problem. The key insight, or aha moment, behind this problem is recognizing that it can be reduced to identifying gaps between consecutive numbers in nums, thanks to the fact that nums is sorted. Instead of iterating over every number in the range, we can skip directly to the next number in nums whenever possible, drastically reducing unnecessary computations. Comparing the approaches, brute force is conceptually simple but highly inefficient for large ranges, as it requires repeatedly checking for missing numbers across the entire range. The set-based approach improves the efficiency of existence checks but comes with additional memory overhead. Binary search could be used to narrow down boundaries within nums, but it adds unnecessary complexity, as the problem can be solved with a straightforward linear traversal. The optimized two-pointer approach stands out because it combines efficiency with minimal overhead. It uses O, n, time and O, 1, extra space, making it well suited for handling large inputs while maintaining clarity and simplicity in implementation. This combination of efficiency and simplicity is why the two-pointer approach is the best choice for this problem. To solve the missing ranges problem, we start by breaking the task into clear steps. First, we initialize an empty list result to store the missing ranges we identify. We also set a variable previous to lower 1. This variable helps us track the last processed number, starting just before the lower bound. Next, we iterate through the sorted input array nums. For each number in nums, we check if there's a gap between the last processed number previous and the current number. If number previous plus 1, it means there's a missing range. We then add this missing range to result. If the gap is a single number, we simply append that number. Otherwise, we format it as a range, like x-y, and add it to the list. After checking for missing ranges within the array, we update previous to the current number being processed. This ensures that previously always tracks the most recent number for subsequent checks. Once all the numbers in nums have been processed, we handle any missing range that might exist at the end of the array. This is the range from previous plus 1 to upper. If such a range exists, we append it to result using the same logic we applied earlier for gaps. Finally, we return the result list, which contains all the missing ranges in the required format. Understanding the efficiency of this algorithm is key. We achieve a single pass through the nums array, which minimizes redundant operations. This gives the algorithm a time complexity of O, n, where n is the size of the input array. There are also important edge cases to handle. For instance, if nums is empty, the entire range from lower to upper is missing and should be returned. If nums fully covers the range, there are no missing ranges, and result remains empty. Finally, gaps at the start or end of the range are accounted for by initializing previous to lower 1 and explicitly checking the final boundary. Additionally, the algorithm formats missing ranges directly during the gap checks, making it efficient in avoiding unnecessary transformations. The algorithm uses simple yet effective data structures. First, the result list is used to store all missing ranges as strings. This choice is natural because it supports sequential appending and allows us to directly store the formatted ranges. Second, the variable previous is crucial for tracking the last processed number. By using only previous in the input array, the algorithm maintains 1 additional space complexity. This means it doesn't require extra memory beyond the list for the output, which keeps it space efficient while still correctly identifying all missing ranges. Let's walk through an example to see how the algorithm works in practice. Suppose we have nums equals 3, 7, 10, with lower equals 1 and upper equals 12. We begin by initializing result as an empty list and setting previous to 0. In the first iteration, the current number is 3, so we check for a gap between previous plus 1 and number 1. This gives us the range, 1, 2, which we format as 1-2 and add to result. We then update previous to 3. Next, in the second iteration, the current number is 7. The gap between previous plus 1 and number 1 is 4, 6. We format this as 4-6 and add it to result, then update previous to 7. In the third iteration, the current number is 10, and the gap, 8, 9, is identified. We add 8-9 to result and update previous to 10. After processing all numbers in nums, we check for a tail range from previous plus 1 to upper. In this case, the range, 11, 12, is missing. We format it as 11-12 and add it to result. At this point, all missing ranges have been identified, and result contains 1-2, 4-6, 8-9, 11-12. This is the final output, which represents all the missing ranges between the lower and upper bounds, given the input array. This Python implementation solves the LeetCode problem number 163, missing ranges efficiently. The goal is to identify all the missing ranges between a given lower and upper bound in a sorted array nums. The find missing ranges function begins by initializing an empty list result to store the missing ranges. A variable previous is set to lower 1, representing the last processed number, starting just below the lower bound. To ensure that the upper bound is included in the evaluation, the function appends upper plus 1 to the nums array. This ensures that the last range up to the upper bound is properly considered. The function then iterates through the numbers in nums. For each number, it checks if there is a gap between previous plus 1 and the current number. If a gap exists, it determines whether the gap represents a single number or a range. A single number is added directly as a string, e.g., 4, while a range is added in the format start-end, e.g., 5-7. After processing each number, previous is updated to the current number to track progress. Finally, the function returns the result list containing all the missing ranges. This implementation handles edge cases like empty arrays, no missing ranges, and various bounds efficiently while maintaining clarity and simplicity. This is the Java implementation of the missing ranges problem. The logic mirrors the provided Python solution, with adjustments for Java syntax and conventions. Notable differences include the use of Java's list interface for the result, explicit type declarations, and array handling with arrays.copyOf to append the upper plus 1 value. The core algorithm remains identical, iterating through the array and identifying ranges based on the difference between consecutive elements. Here, we start with the example where nums equals 3, 5, 10, lower equals 0, and upper equals 12. To simplify our logic, we append upper plus 1 to the nums array, making it 3, 5, 10, 13. We then initialize an empty list result to store the missing ranges, and set previous to lower 1, which is -1. Now, in the first iteration, we check the first number in nums, which is 3. Since 3 is greater than previous plus 1, or -1 plus 1, there is a gap. The missing range is from previous plus 1 to number 1, which gives us 0-2. We add this range to result and update previous to 3. In the second iteration, the next number is 5. Again, because 5 is greater than previous plus 1, or 3 plus 1, there is another gap. This time, the gap is just the single number 4, so we add 4 to result and update previous to 5. As we continue, the third number in nums is 10. Since 10 is greater than previous plus 1, or 5 plus 1, we identify another gap. The missing range spans from 6 to 9, so we add 6-9 to result and update previous to 10. Finally, the last number in nums is 13. Since 13 is greater than previous plus 1, or 10 plus 1, there is one more gap. The range is from 11 to 12, so we add 11-12 to result and update previous to 13. At the end of the process, our result contains all the missing ranges, 0-2, 4, 6-9, 11-12. This is the final output for this example. Now, let's look at another example where nums equals 1, 3, 7, lower equals 1, and upper equals 10. As before, we append upper plus 1 to nums, making it 1, 3, 7, 11. We initialize result as an empty list and set previous to lower 1, which is 0. In the first iteration, the first number in nums is 1. Since 1 is not greater than previous plus 1, or 0 plus 1, there is no gap, so we simply update previous to 1. In the second iteration, the next number is 3. This time, 3 is greater than previous plus 1, or 1 plus 1, so we find a gap. The missing value is the single number 2, so we add 2 to result and update previous to 3. In the third iteration, the next number in nums is 7. Since 7 is greater than previous plus 1, or 3 plus 1, there is another gap. This gap spans from 4 to 6, so we add 4-6 to result and update previous to 7. Finally, the last number in nums is 11. Again, since 11 is greater than previous plus 1, or 7 plus 1, we identify one more gap. The missing range is from 8 to 10, so we add 8-10 to result and update previous to 11. The final output for this example is 2, 4-6, 8-10. In the final example, we have nums equals, lower equals 1, and upper equals 3. Since nums is empty, we directly append upper plus 1 to it, resulting in nums equals 4. We initialize result as an empty list and set previous to lower 1, which is 0. In the first and only iteration, the first number in nums is 4. Since 4 is greater than previous plus 1, or 0 plus 1, we find a gap. The missing range spans from 1 to 3, so we add 1-3 to result and update previous to 4. With no more numbers to process, the final output for this example is 1-3. The time complexity of this solution is O(n), where n is the length of the input list nums. Let's break this down. First, appending upper plus 1 to the nums array is an O(1) operation since it only involves adding a single element to the end of the list. Next, we iterate over the modified nums array, which contains n plus 1 elements, including the appended upper plus 1. For each element, we perform a constant amount of work, such as checking for gaps between consecutive numbers and appending ranges to the result list. Appending to a list in Python is an amortized O(1) operation, so this does not significantly impact the complexity. Additionally, determining the range between two numbers, whether it's a single number or a range like a -b, is also done in constant time. Even the string concatenation for ranges is efficient, as the number of digits being combined is relatively small for typical inputs. Overall, the dominant factor in the time complexity comes from iterating through the nums array, which gives us O(n). Thus, the primary driver of the time complexity is the iteration over the nums array, which is O(n). Now, moving to space complexity, the solution requires O(n) space as well. First, the modification of the nums array by appending upper plus 1 adds only a constant amount of memory, so this is O(1). The result list, however, stores the missing ranges. In the worst case, if nums is empty and all numbers between lower and upper are missing, the result list will contain upper lower plus 1 entries. For typical inputs, this is proportional to the size of the nums array, making it O(n). Finally, the temporary variables, such as previous, number, and the strings used for ranges, use constant memory, which is O(1). Therefore, the space complexity is dominated by the size of the result list, giving us O(n). The overall space complexity is determined by the result list, which is O(n) in the worst case. Let's compare this optimized approach to a brute force or naive method. A naive solution would involve iterating through the entire range from lower to upper and checking for missing numbers one by one. This would result in a time complexity of O upper lower plus 1, which can be significantly larger than O(n) when the range is sparse. Additionally, the space complexity of the naive approach would also be O upper lower plus 1 for the output list in the worst case. In contrast, the optimized solution leverages the sorted nature of nums and focuses only on the gaps. This reduces the time complexity to O(n) and the space complexity to O, n, where n is the size of the input list nums. This makes the solution much more efficient for sparse ranges. Now, let's analyze the best, average, and worst cases for the algorithm. In the best case, if nums already covers the entire range from lower to upper with no missing ranges, the algorithm still needs to iterate through all elements of nums. As a result, the time complexity remains O, n. For the average case, where nums is sparse and covers parts of the range, the algorithm efficiently identifies gaps in O, n, time. The space complexity in this case remains O, n, due to the result list storing missing ranges. In the worst case, if nums is completely empty, the algorithm generates all missing values from lower to upper. Here, the time complexity is O, n, and the space complexity is O, n, where n equals upper, lower plus 1. While the output size is the same as the naive approach in this scenario, the optimized method avoids unnecessary iterations over the entire range, making it more efficient. Finally, let's confirm the time and space complexity mathematically. The for loop processes each of the n plus 1 elements in the modified nums array. During each iteration, the algorithm performs constant time operations like condition checks, appending to the result list, and updating the previous variable. Together, these operations result in a total time complexity of O, n. For space complexity, the result list dominates the memory usage. In the worst case, it contains up to upper lower plus 1 ranges, which is proportional to the size of nums for most inputs, giving us O, n. Temporary variables and the modification of nums add negligible memory overhead, so the overall space complexity remains O, n. This combination of O, n, time and O, n, space ensures the solution is both efficient and scalable. Common mistakes in the missing ranges problem often revolve around edge cases, consecutive numbers, and boundary calculations. For example, failing to handle an empty input array or when the entire range is already covered can result in runtime errors or incorrect results. To address this, make sure you explicitly check scenarios like nums equals, or when nums spans from lower to upper completely. Another common issue occurs when consecutive numbers are mishandled. If two numbers are back-to-back, their gap might be skipped or improperly formatted. You can resolve this by ensuring your logic accounts for differences like I plus 1, I equals 2. Additionally, off-by-one errors in range boundaries can cause mistakes, so be diligent about whether your bounds are inclusive or exclusive. Lastly, avoid brute force methods that iterate through every number in large ranges. Instead, leverage the sorted nature of the nums array to compute ranges more efficiently. String formatting is another area where mistakes can arise, particularly when distinguishing between single values and ranges. For example, the output, 5 versus 5-7, must follow consistent formatting logic to avoid malformed strings. A good strategy is to handle single numbers and ranges separately in your code. From an interview perspective, this problem centers on identifying missing intervals, making it essential to optimize your solution by using the sorted property of nums. You can also think of this as a variation of the merge intervals pattern, except here, you're identifying the gaps between intervals instead of merging them. Always test your solution with edge cases, such as when nums is empty, contains duplicates, or already spans the entire range. In interviews, it's also a good idea to clarify whether the range is inclusive or exclusive and confirm the expected output format with examples. The missing ranges problem shares similarities with several other LeetCode problems. For instance, LeetCode 57, Insert Interval, involves working with intervals but focuses more on merging rather than finding gaps. LeetCode 228, Summary Ranges, is directly related since it involves formatting ranges from a sorted array, much like this problem. Naturally, LeetCode 163, Missing Ranges, is the specific problem we're discussing here. Additionally, LeetCode 448, Find All Numbers Disappeared in an Array, is related because it also deals with finding missing elements, though it focuses on unsorted arrays. By studying these problems, you can deepen your understanding of interval-based patterns and apply similar techniques to a wide variety of scenarios. There are several alternative approaches to solving the missing ranges problem, each with its own trade-offs. The optimized two-pointer approach is a popular choice, where you use two pointers to iterate through the nums array while keeping track of the lower and upper bounds. This method is efficient, with O, n, complexity, but requires careful handling of gaps and edge cases. Another option is the binary search approach, which can be useful for large nums arrays. By using binary search to locate positions within the range, you can optimize certain operations, though this approach increases implementation complexity. Finally, there's the set-based brute force method, where you use a set to store nums and iterate through the entire range from lower to upper, checking for missing values. While simple to implement, this method becomes inefficient for large ranges due to its O, n plus m, complexity, where n is the size of nums and m is the range size. Great job! In summary, we tackled the missing ranges problem by leveraging an efficient iterative approach. Remember to practice similar problems to master range-based algorithms and edge case handling. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!